On the morning of December 8th, a subtle but important recalculation was issued by NASA's Jet Propulsion Laboratory. The orbital trajectory of 3I Atlas had shifted again, not in a way that would spark immediate public concern, but enough to send a ripple through every observatory tracking its motion. The new arc brings the interstellar object slightly closer to Earth, cutting down the projected flyby distance by a small but significant margin. The change is measured in fractions of an astronomical unit, but when you're dealing with objects travelling hundreds of thousands of kilometres per hour, even small deviations become cause for deep review. This wasn't a case of bad math. The previous predictions were sound, based on thousands of precise observations from observatories all over the world. But 3I Atlas has consistently defied expectations. From the moment it slingshotted around the Sun on October 30th, it has shown signs of non-gravitational behaviour, accelerations, deviations and emissions that cannot be easily explained by solar pressure or outgassing alone. And now, for the third time in less than 4 weeks, the object's projected path has changed once again. The most recent update placed its closest approach on December 19th, still at a safe distance from Earth, but closer than originally thought. What makes this latest adjustment so intriguing is the pattern of the shift. It's not chaotic, it's not drifting randomly. Instead, the motion appears smooth, continuous, as if some consistent but unmodelled force is gently nudging the object's trajectory over time. If 3I Atlas were merely venting gas from its sunward side like a typical comet, we'd expect to see some wobble in its motion, torque, spin changes, or random accelerations depending on the orientation of its jets. But that's not what the data shows. Instead, the motion is almost purposeful, not in the sense of intelligence or control, but in the sense of clarity. It moves in a line that suggests awareness of forces we haven't fully accounted for. The consistency of the arc, the timing of the changes, and the fact that each update has nudged it just a little closer to Earth. These elements together are difficult to ignore. Orbital analysts at ESA and the Minor Planet Center have confirmed the same trend. Using data from the Solar Orbiter, ground-based radar imaging, and optical tracking from Hawaii, Chile and Spain, the updated curve now puts 3I Atlas within a narrower corridor of Earth's magnetic influence. It won't hit, but it will pass close enough that the planet's outermost electromagnetic fields, the magnetopause and bow shock, will likely feel its presence. This isn't a direct threat. It's not the kind of encounter that causes panic, but it does move the conversation into new territory. What matters now is interaction, not impact. When an interstellar object passes close to a planet, even at safe distances, its high-velocity motion, mass-loss trail, and potential electromagnetic behaviour can couple with the environment around it. This has implications for satellite tracking, atmospheric sensors, and even the upper ionosphere. And it's precisely why this updated trajectory is being watched so carefully. Not because Earth is in danger, but because Earth is now part of the active equation. The real question isn't how close 3I Atlas will get. It's what will happen during that close pass. Will its tail flicker as it skims past the magnetic lines of our planet? Will the dust it sheds interact with the solar wind around Earth's field? Will we see auroras in places we don't expect, or electrical interference in places we've never measured? As we move closer to December 19th, the science community is preparing to monitor every possible variable, because this trajectory change, while small, is a signal, not of danger, but of importance. 3I Atlas is coming, and now it's closer than we planned for. When tracking interstellar objects like 3I Atlas, most astronomers focus on proximity, how close the object will come to Earth in terms of kilometres. But there's another variable just as important, angle of approach, and as of the latest data recalibration on December 8th, that angle has changed in a way that's now drawing quiet, serious attention. 3I Atlas is not just passing nearby, it's doing so along a vector that now aligns with Earth's magnetic north. That may sound abstract, but in practical terms, it means that the object's path through the inner solar system is now pointed almost directly at one of Earth's magnetic poles, the energetic gateway through which high-energy particles interact with our atmosphere. Earth's magnetic field isn't just a passive shield, it's a dynamic structure, constantly interacting with the solar wind, filtering cosmic radiation, and forming protective layers like the magnetosphere and ionosphere. The poles, particularly the magnetic north, are regions where charged particles from space enter most directly. These are the zones responsible for auroras, but also for sudden changes in electrical conductivity in the upper atmosphere, satellite interference and radio blackouts. So when an interstellar object's approach aligns with one of these poles, it creates conditions that have never been tested and cannot be modelled with precision. 3I Atlas has already demonstrated unusual electromagnetic behaviour. Just days earlier, microwave pulses were detected emanating from its vicinity. Its tail is filled with ultrafine carbon-rich particles, the kind known to interact with magnetic fields. And now its projected line of motion appears to intersect the region above Earth where the magnetosphere is weakest and most exposed, the polar cusp. The polar cusp is a funnel-shaped opening in Earth's magnetic field. It allows solar wind particles to penetrate deeper into the atmosphere than usual. When objects emitting charged dust, radiation, or even electromagnetic pulses align with this opening, unexpected things can happen. In the case of 3I Atlas, the alignment doesn't imply a direct entry into our atmosphere. It's far too distant for that. But it does suggest that whatever this object is shedding could directly interact with the magnetic scaffolding that protects Earth. Why is that significant? Because almost everything we rely on, GPS, communications, navigation systems, weather satellites, depends on the stability of the magnetosphere, and when unusual material enters the system from above, especially from an angle that pours it directly into the polar funnels, it can lead to minor but measurable disruptions. This has happened before with solar flares and high-energy cosmic bursts, but never before has it happened with an interstellar object approaching in such a direct pole-facing alignment. There is also an unknown: how Earth's magnetosphere will respond to the unique composition of 3I Atlas. This isn't just another icy comet. Its coma contains unusually conductive materials. Its surface exhibits reflectivity patterns that hint at metal-rich compounds, and if these materials interact with Earth's magnetic layers, even from a safe distance, they could create temporary distortions in local magnetic field lines, possibly triggering brief anomalies in satellite telemetry or ground-based magnetometers. Already, some modelling labs in Finland, Canada and Norway, regions close to Earth's magnetic north, are preparing to deploy additional ionospheric sensors during the object's closest pass. They're not expecting catastrophe, but they are expecting data they've never seen before. This alignment is rare. It's not something we can recreate or simulate in a lab. An interstellar object passing within 1.6 AU of Earth, with its vector pointed directly at our most sensitive magnetic region. This is a natural experiment, one that could either pass in silence or teach us something brand new about the invisible shields that protect our planet. And the countdown has already begun. In the early hours of December 8th, a joint observation between the James Webb Space Telescope and Chile's ALMA radio array confirmed something that has been quietly building over the last 10 days. 3I Atlas is losing mass, and that mass loss is accelerating. This isn't just a slight increase in outgassing, it's a measured curve that's now rising faster than any model would predict for an object this far from the Sun. Normally, after perihelion, the point of closest approach to the Sun, comets begin to quiet down. They vent less gas, the coma shrinks, and the dust tails start to disperse. The Sun has done its work and the object begins to settle into its outbound arc. But that's not what's happening here. Instead, 3I Atlas is behaving like a machine shifting into a higher gear after the point where it should be slowing down. Astronomers now estimate that its current rate of mass loss is exceeding 5 billion kilograms per week, a rate that has tripled since the first week of November. But the object isn't breaking apart. It's not disintegrating. Its structure, at least visually, remains intact. That's the mystery. A typical comet under this kind of stress would begin to fragment. Pieces would fly off, brightness would become erratic, and its shape would become more chaotic. 3I Atlas is doing the opposite. It's stable, structured, and shedding mass at a pace that suggests internal energy is still being released. So where is the energy coming from? At a distance of over 1.6 astronomical units, sunlight alone shouldn't be enough. Solar heating falls off dramatically with distance, and the amount of energy reaching the object now is far less than it received during its October perihelion. That means something else must be driving the process, and it leaves scientists with a few uncomfortable options. One explanation is that 3I Atlas is harbouring a layer of super volatile ices. compounds like carbon monoxide or carbonyl sulfide that sublimate at much lower temperatures than water or carbon dioxide. If true, the object might be built from a composition unlike anything in our solar system. But this theory has one major flaw. The spectral data doesn't fully support it. The emissions being detected are largely carbon dioxide and water vapour, and the ratios haven't changed dramatically. What has changed is the rate at which those compounds are being expelled, suggesting an amplifier, not a trigger. Another possibility is internal heating. If 3I Atlas absorbed energy during perihelion and is now releasing it from beneath a crust or layered shell, it might explain the delayed acceleration in mass loss. But again, this only makes sense if the object has an insulating structure, perhaps with materials we don't associate with comets. Infrared readings show regions of thermal variance across the surface, with some parts cooling, while others are heating up. This is not uniform sublimation. This looks selective, focused. That raises the more exotic theory, the one that's still whispered more than spoken. Is 3I Atlas releasing energy deliberately? The idea isn't about intelligence, it's about design. If the object has a structure that allows it to store heat, redirect it, or even control its venting behaviour, then what we're seeing might be an engineered function, not just thermal breakdown, jets that turn on at precise intervals, mass loss that accelerates with alignment, energy release that favours directional thrust. All of these patterns match what's being observed now, and here's the kicker, the dust tail is not dispersing. Despite this dramatic loss of material, the expelled particles are remaining in tight formation, focused along two main jets. It's as if the mass loss isn't waste, but output. In short, 3I Atlas is now in a phase of active transformation. Whether that transformation is geological, chemical, or something entirely unknown remains an open question. But the one thing no one doubts anymore is this. The object is accelerating its behaviour as it nears Earth, and we've never seen anything like it. One of the most striking observations in recent days doesn't involve light curves or chemical ratios. It's something far more visual, something any telescope can confirm with a long enough exposure. The dust jets of 3I Atlas are now rotating, and they're doing so in a way that has no clear precedent in cometary physics. Since late November, astronomers have noticed that the twin jets emanating from opposite sides of the nucleus were not stationary. They weren't fixed outflows or simple geysers of sublimating gas. Instead, they were slowly pivoting, their orientation shifting over hours, almost like arms sweeping across space. At first, this was assumed to be a result of the object's rotation, a natural effect as surface vents on a spinning nucleus change their position relative to Earth and the Sun. But as more data came in, a pattern began to emerge, and that pattern broke the model completely. The jets were not spinning randomly or with wobble. They were rotating with synchronized precision, symmetrical in timing and angle, as if the entire system was behaving more like a gimbal or turret than a tumbling piece of rock. Observatories in Hawaii, Chile, and the Canary Islands all confirmed it. The twin jets maintain a constant angle of separation, roughly 180 degrees, while completing a visible sweep every few hours. Not only that, but the rotation rate of the jets appears to be increasing, even as the object loses mass. That makes no sense under traditional sublimation theory. In natural comets, jets form when solar heat penetrates surface cracks, causing volatile ices to erupt outward. These vents open and close chaotically. Their direction is based on pressure, surface geometry, and spin rate. But 3I Atlas's jets are ordered. The rotation isn't caused by the body spinning. It's caused by something deeper, possibly internal, coordinating how and where gas and dust are expelled. The implications are enormous. If the jets are rotating independently of the object's spin, then there must be some mechanism of control beneath the surface. That could mean the object has internal chambers, pressure pockets that vent gas through rotating valves or shifting conduits. It might mean there's an axis of internal symmetry, a structure within the nucleus that stabilizes the motion of gas even as the object moves through space. Or, and this is what excites and unsettles many observers, it could suggest design. Rotating jets are a concept more familiar to spacecraft engineers than planetary scientists. In artificial systems, gimbaled nozzles are used to steer thrust, allowing rockets to maintain or change direction. The pattern observed in 3I Atlas resembles a vectoring exhaust system. with jets that sweep back and forth to maintain balance or adjust heading. So, what would that mean for a supposedly natural object? It could mean that the mass ejection isn't just random venting, it's thrust. Controlled thrust. A way to steer or stabilize the object as it navigates the inner solar system. If the outgassing is being focused into rotating jets, 3I Atlas may be shaping its own trajectory, using internal mechanisms rather than responding passively to solar pressure. That would explain its smooth acceleration. It would explain its lack of fragmentation, and it would explain why its spin rate is stable, even as other forces act upon it. But the question remains, is this natural or engineered? Some scientists are now looking into exotic explanations, such as subsurface gas cavities shaped by non-random internal layering, or even magnetic fields within the object that rotate venting pathways through charged dust control. Others are less cautious, suggesting we may be witnessing a self-stabilizing system not unlike a basic propulsion array, built for balance, not travel. Regardless of origin, one thing is now clear. 3I Atlas's dust jets are behaving with intention, not randomness. And whatever is driving that rotation, natural, artificial, or something in between, it means we're not dealing with a typical comet. We're watching something more complex, something we've never seen before. One of the strangest and most persistent features of 3I Atlas is something that shouldn't even exist this late in its journey, an anti-tail, a stream of material pointing toward the sun instead of away from it. And as of the most recent images captured on December 8th, that anti-tail is not fading. It's strengthening, sharpening, holding its shape far longer than any natural outflow model would allow. In cometary science, anti-tails are rare, but not unheard of. They are usually explained as optical illusions, a trick of geometry caused by Earth's position relative to the plane of the comet's orbit. Essentially, what appears to be a backward-facing tail is just sunlight, reflecting off a trail of dust the comet dropped days or weeks earlier, which happens to line up with our viewing angle at the time. But these features are short-lived, dependent entirely on perspective. They do not persist across multiple days, let alone multiple Earth-based angles. That's what makes 3I Atlas different. Since late November, observers across several continents have been reporting the same thing, a defined anti-tail that holds steady even as Earth's position shifts. The tail doesn't blur, bend, or vanish with orbital drift. It remains visible, tight, bright, and curving back toward the very star that should have vaporized it weeks ago. As of December 8th, its alignment now appears to point directly down the Sun-Earth axis, forming what can only be described as a reverse jet. Not a passive trail, but an active stream. This is not normal. Under standard physics, solar radiation pressure pushes all dust and gas away from the sun. That's what gives comets their classic sweeping tails, long arcs stretching behind them as they move through space. Even large dust particles, though heavier than gas molecules, are still subject to that outward push. So for a comet to display a tail pointing sunward, one of two things must be true. Either the particles are so massive that radiation can't move them, which would make the tail diffuse and faint, or the material is being actively ejected toward the sun, against the force of solar wind. In 3I Atlas's case, the anti-tail is bright, thin, and coherent, suggesting not only is it dense, but it's also possibly being expelled with energy. In other words, this might not be a remnant. It might be a deliberate directional feature. That possibility changes everything. If the anti-tail is a real structure and not just a perspective trick, it suggests that the object is exerting force toward the sun, and if it's doing that, it's creating thrust in the opposite direction, away from the sun toward its outbound path. In basic physics, that's Newton's third law in action. For every action, an equal and opposite reaction. Expel mass sunward, and you move sunwards opposite. This is how rockets work. It's how propulsion works. So what happens when a comet does it? This phenomenon has prompted speculation that 3I Atlas is maneuvering, not tumbling, that it's directing mass ejection in specific angles to maintain stability, or even to change its course slightly. And that tail, rather than being a passive indicator of motion, might be part of a system, a functional structure used to control acceleration. Some astrophysicists are now running thrust curve simulations based on the orientation of the anti-tail and the timing of the object's non-gravitational shifts. The early results are, at the very least, curious. the vectors match. Even more strange is what's inside the anti-tail. Spectral analysis shows elevated carbon content, not fine dust, but micron-sized particles with high reflectivity. Materials that could, under the right conditions, behave more like conductive chaff than passive debris. That adds an electromagnetic layer to the puzzle. If the anti-tail is charged, it might be interacting with solar fields, not just moving through them. In simple terms, this tail is pushing back. And now, Earth is sitting downstream. In deep space, not all dust is created equal. Some grains are reflective and inert, others are chemically reactive, carrying volatiles or metals. But every once in a while an object shows signs of something far stranger. Dust that behaves like it was forged, not just formed. And that's exactly what 3i Atlas is now revealing. The latest infrared readings, taken between December 6th and 8th by the James Webb Space Telescope and confirmed by data from ESA's solar orbiter, have shown consistent thermal signatures pointing to carbon-rich particulate matter in the object's coma and tail. These aren't just random dust grains. These are dense, structured carbon-based materials, and their behavior in sunlight is rewriting what scientists thought they understood about interstellar debris. When comets eject material, the composition of that material is usually a mix of simple ices, water, carbon dioxide, methane, along with silicate dust, organics, and trace metals. In solar system comets, carbon is present but typically in low ratios and spread thinly across larger, more inert particles. It doesn't dominate, it doesn't define structure, and it almost never appears in high-temperature infrared bands, but with 3i Atlas, that's what we're seeing. Infrared spectroscopy across multiple wavelengths has revealed strong emission spikes consistent with amorphous carbon, graphite, and even possible carbon composites. Materials that respond very differently to heat and radiation than typical comet dust. These signatures are visible at temperatures that suggest the dust is retaining heat, not just reflecting or re-radiating it. That's important, because it means the object is not only expelling mass, it's expelling material that could conduct, store, or even redirect energy. This changes how scientists model its interaction with both solar radiation and magnetic fields. Carbon-rich particles have an entirely different relationship with their environment. They absorb more heat, they scatter light less efficiently, and, most notably, they can carry charge. That means they can respond to electromagnetic fields in space, creating interactions that go far beyond gravity or radiation pressure. In 3i Atlas's case, these particles appear to be flowing along distinct vectors, not dispersing randomly, but forming concentrated arcs, especially along the primary tail and the anti-tail. That's not how comet dust is supposed to behave. The pattern emerging now resembles more of a guided flow than a passive emission. It's as if the carbon dust is either being directed by internal electromagnetic forces from the object, or is reacting to external fields in a way that compresses and shapes its trajectory. Some scientists are even comparing the structures seen in recent thermal overlays to ionized wake trails, the kind left behind by spacecraft engines in vacuum test chambers. So where is this carbon coming from? The short answer is, we don't know. Some hypotheses suggest that 3i Atlas formed in a cold, carbon-rich system beyond our own, one where graphite and organics formed more abundantly than water ice. Others propose that this carbon is the result of long-term interstellar radiation processing, where cosmic rays transformed basic molecules into more complex carbon frameworks over millions of years. But both of those theories have trouble explaining the purity and concentration of what we're seeing now. The carbon signature isn't diluted, it's dominant. More speculative theories suggest something more engineered, materials designed to handle extreme radiation, retain structure after perihelion, and respond to magnetic forces. If that's the case, these carbon particles might be part of a controlled system, not just byproducts of heat. That would mean 3i Atlas is built differently, maybe even intentionally. For now, what's clear is this: 3i Atlas is not shedding ordinary dust. It's leaving a trail of carbon that behaves more like dark circuitry than comet tail debris. And with Earth directly in the path of that trail on December 19th, researchers are scrambling to understand what this material might do when it intersects our upper atmosphere, or our satellites. We've never tracked an object like this before, and its dust may be the key to understanding what, or who, sent it. Over the past 72 hours, a subtle but consistent signal has begun to appear across global monitoring arrays. It's not an image, it's not a visible trail, it's a pulse, low-frequency microwave energy that seems to be radiating from the region of space surrounding 3I Atlas. And while no one is jumping to conclusions, the pattern is enough to trigger a quiet alert across multiple observatories. The first detections came from Australia's CSIRO facility, home to one of the Southern Hemisphere's most sensitive microwave listening stations. On the night of December the 6th, their instruments picked up a brief fluctuation in the 120-300 MHz band, a window typically associated with solar storm activity, but the sun, at that time, was quiet. The source appeared to be offset from the solar plane and moving, tracking slightly faster than background cosmic noise. Then came confirmation. 2 hours later, the same pulse pattern was picked up by the Murchison Wide Field Array, also in Australia, followed by a third reading from a French deep space monitoring station near Toulouse. All pointed to the same location, the sky coordinates occupied by 3I Atlas. The pulses were weak, nearly buried in background radiation, but they were structured. Not in a signal sense, not modulated data, but spaced in a rhythm. 5 pulses, then silence, then 5 again, a repeating pattern every 37 minutes. That rhythm raised eyebrows. Natural cosmic microwave bursts are usually chaotic. They spike and fade with no regularity. Signatures of collapsed stars, black hole jets, or turbulent solar wind. But 3I Atlas's pulse is calm, evenly spaced, and tightly bound to its physical position, and it's growing stronger. Each new round of pulses is brighter than the last, still faint, but edging upward in signal-to-noise ratio with every new observation. So what could it be? One theory is thermal stress. As the object sheds mass, expands gas, and heats unevenly across its surface, it could produce intermittent microwave emissions, a kind of radiative burp from venting materials. Another theory points to carbon-rich dust particles in the tail, particles that, when struck by solar wind, might emit brief microwave signatures as they charge and discharge. That would make the pulses a plasma interaction, not a signal. But both of those explanations fail to answer the question of timing. Why would these pulses occur with such regularity? And why now, just as 3I Atlas begins to rotate its jets and accelerate its mass loss? The synchronicity has some observers quietly proposing a more deliberate model. Not intelligent transmission, but active electromagnetic behavior. In this scenario, the object isn't sending messages, it's managing energy. The pulses would be a byproduct of some internal process, like capacitive discharge from rotating jets, or a surface mechanism shedding excess charge into space. It would be the equivalent of a natural capacitor flickering under strain, releasing just enough charge to prevent breakdown, and doing so at precise intervals tied to rotation or solar exposure. If this is what's happening, then the object is more than stable. It's regulating itself. Further complicating the picture, the direction of the pulse's strongest projection, its beam, if one can call it that, appears to be narrowing. Observations on December 8th show a shift of the strongest detection zone toward Earth's orbital path. Still distant, still millions of kilometers away, but beginning to focus inward. This is a red flag, not because it suggests intent, but because it hints at coupling. Something about Earth's proximity may be drawing or reflecting part of the pulse energy. What happens when Earth intersects that narrow corridor remains unknown. No damage is expected. This is low-energy radiation, but the signature itself is enough to warrant expanded monitoring from NOAA, NASA's Deep Space Network, and European polar orbiting satellites. All now have one directive: watch for fluctuation and track the pattern. Because if these pulses continue, or grow in intensity, we may be witnessing the first electromagnetic behavior from an interstellar object that doesn't just pass by, it communicates with its environment. On December 8th, a subtle but eerie calm descended over one of the most dynamic regions protecting our planet, Earth's magnetosphere. This invisible shield of charged particles and magnetic currents is always in motion, constantly shifting in response to solar winds, coronal mass ejections, and interplanetary magnetic field fluctuations. But today, something is different. The data shows silence. It's the kind of quiet that unsettles scientists. From satellites in low Earth orbit to deep space observatories like the Parker Solar Probe and the Solar Dynamics Observatory, all major instruments report the same thing: a sharp drop in turbulence within Earth's magnetic field. Plasma densities are down. The bow shock, the region where solar wind normally crashes into Earth's magnetic defences, is unusually smooth. Even the Van Allen belts, often agitated by charged solar particles, show minimal activity. At first glance, this might seem like good news. After all, space weather quiet means fewer disruptions to satellites, no geomagnetic storms, and stable radio transmissions. But in the context of what's happening beyond our planet, specifically with 3I Atlas, this sudden stillness is prompting a very different question. Is Earth's magnetosphere responding to something approaching it? This isn't speculation. The last time such magnetospheric stillness was recorded was in the hours before the 2003 Halloween solar storms, right before a massive CME struck Earth and overwhelmed the system. But this time, there's no solar flare, no CME, no sunspot. The sun is calm, and yet Earth's magnetic field is acting as if it's bracing for something. Here's where things get more unusual. The Parker Solar Probe, which recently passed through a region of space not far from 3I Atlas's outbound trail, recorded a localized dip in plasma turbulence, a kind of vacuum pocket where the usual solar wind was interrupted. The pocket wasn't large, but it was precisely where 3I Atlas had passed just days before. That same quiet, the same suppression of background charge, now seems to be forming ahead of Earth in the direction of 3I Atlas's approach. To be clear, no one is suggesting the object is draining Earth's magnetic energy. But several labs are now exploring the possibility of magnetospheric compression caused by field interference, where charged particles, especially carbon-rich conductive dust, could create a barrier or absorb solar wind momentum before it reaches Earth. If that's happening, Earth's magnetosphere might be reacting to pressure it doesn't understand and going silent as a result. Some models call this pre-coupling, a state where two magnetic or plasma systems approach each other and begin to interact subtly before physical proximity occurs. The analogy is two weather fronts converging. Before the storm hits, there's a strange calm, a compression of forces, a flattening of air movement. In space weather terms, Earth might now be entering that calm, and the timing could not be more precise. 3I Atlas is still over 1.6 AU away, but its tail, its jets, and now possibly its low-frequency microwave emissions are already affecting the region around Earth. The magnetosphere isn't fighting back, it's pulling inward, coiling quietly, almost as if preparing for an energetic handshake. What makes this more compelling is that Earth's polar magnetometers, particularly in northern Canada and Finland, have reported an increase in magnetic alignment, not agitation, alignment. Field lines are drawing tighter together, behaving with a kind of forced coherence. The chaos of solar noise is being replaced by symmetry, and that, in nature, rarely happens without cause. It's too early to say whether this calm is the beginning of a larger event or simply a lull before the next solar fluctuation. But as 3I Atlas continues its approach, scientists are now watching for any further anomalies in Earth's magnetic field, not just for what they might tell us about our planet's defences, but for what they might reveal about the strange silent pressure arriving from deep space, because sometimes the scariest sound in the universe is none at all. Every comet has a halo, a cloud of gas and dust that surrounds its core as it sublimates under solar heat. This glowing shell is called the coma, and it typically expands outward in all directions, forming a spherical or elliptical shape that drifts away from the comet's nucleus. The process is simple. Sunlight hits the surface, volatile ices vaporize, and that gas pushes outward, carrying dust with it. It's chaotic, but predictable, unless you're looking at 3I Atlas, because as of December 8th, something very strange is happening to its coma. It's not expanding, it's compressing, and worse, it's compressing in the wrong direction. The latest composite images from Chile's Gemini Observatory and Europe's ESOHO satellite show a surprising asymmetry around the nucleus of 3I Atlas. The sunlit side, the portion of the comet facing away from Earth, is behaving normally with gas and dust dispersing outward into the solar wind. But on the Earth-facing side, the coma appears compressed, even flattened, as though something is pushing against it or pulling it inward. This is not how comas behave. Under normal conditions, the sun-facing side of a comet is always more active. The increased solar radiation causes heavier sublimation, leading to outgassing that expands the coma outward and away from the Sun, on the opposite side of the night side as activity is typically weaker. But 3I Atlas is showing reversed pressure dynamics. The coma is being squeezed inward, not just toward the nucleus, but specifically toward the side facing Earth. So what's doing the squeezing? Initial theories pointed to solar wind variations. Perhaps a fast stream of particles from the Sun was colliding with the tail and pushing back against the dust flow, but solar data shows nothing of the sort. The Sun has been relatively calm since December 6th. No coronal mass ejections, no solar flares, no changes in solar wind density or direction, strong enough to cause the kind of compression being observed. That leaves only one possibility: local field interaction. Plasma physicists are now exploring the idea that the coma is being influenced by a localized magnetic disturbance. The compression pattern resembles what's seen when a charged gas cloud encounters a magnetic barrier, such as Earth's magnetopause or the edge of a planetary magnetosphere. In these cases, particles are redirected, slowed, or trapped, forming a visible boundary layer, but there's no planet near 3I Atlas, so where is the barrier coming from? The emerging hypothesis is unsettling. Some researchers believe the compression is being caused by the object itself, or more precisely by its own electromagnetic signature. If 3I Atlas is emitting or carrying a localized magnetic field, generated either by its structure, internal composition, or as a byproduct of sustained energy emission, it could be shaping its coma intentionally, bending dust and gas flows into organized forms. This would explain not only the compression, but also the persistence of jets, the formation of a directional anti-tail, and the tight coherence of carbon-rich dust. It would mean that the coma is no longer passive, it's being sculpted, held in place, or even weaponized. And here's what makes it more than a theoretical exercise. The Earth-facing side of the coma is the only region showing this pressure collapse, which means either 3I Atlas is focusing some type of energetic interaction in our direction, or it's responding to Earth's own magnetic field at a distance. Either way, the timing is no longer coincidental. As the object enters alignment with Earth, its coma begins to tighten, deform, and narrow. If this compression continues, Earth may be struck, not physically but energetically, by a stream of highly organized dust or particles, potentially charged or magnetically active. The outcome of such an interaction is unknown. It could pass by unnoticed, or it could trigger measurable disturbances in Earth's ionosphere, communication systems, or satellite operations. Because in the vacuum of space, motion is never just motion, it's message. And 3I Atlas's coma may now be pointing one directly at us. It was first seen weeks ago, a sharp, unexpected burst of light bouncing off the surface of 3I Atlas. Observers called it a reflectivity spike, a sudden and temporary increase in the amount of sunlight the object was reflecting toward Earth-based telescopes. At the time, many assumed it was a glitch, or perhaps an unusually bright dust jet momentarily catching the sun. But now, on December 8th, it's happening again, and this time it's sustained. Across observatories in Arizona, Chile, and Tenerife, a synchronized flare in visual brightness was detected from the direction of 3I Atlas just after 3 a.m. GMT. Instruments sensitive to albedo, the measure of an object's reflective properties, showed a doubling in apparent reflectivity within a 4-minute window. Not only did the object brighten, but the nature of the reflection changed. It wasn't diffuse, like scattered ice. It was sharp, angular, like polished metal catching the sun. That's not a normal behavior for cometary surfaces. Most comets are coated in dark, dusty material. Their surfaces are irregular, porous, and uneven. Even when ice is exposed, it tends to be rough and granulated, absorbing more light than it reflects. What scientists are now seeing with 3I Atlas doesn't fit that picture. The object appears to redirect sunlight along very specific angles, as if portions of it are flat, geometric, or layered with something highly reflective. Worse still, the spike isn't random anymore. This marks the second time it's occurred at nearly the same point in the object's rotation. Time-stamped brightness data from previous observations match closely with the December 8th flare, suggesting that a specific face or surface of the object is responsible. And that means this isn't just dust scattering light. This is a repeating reflective structure, possibly embedded in or protruding from the nucleus. So what could be causing it? One explanation is the exposure of a crystalline surface, a sheet of pure ice, fractured and smoothed by prior outgassing, now facing the Sun during part of the rotation cycle. Another theory involves metallic compounds, such as nickel-iron mixtures, which can survive perihelion and remain intact on certain types of interstellar debris. But both of those materials would still scatter light unless polished or engineered to a flat geometry. That brings us to a more radical idea. The reflectivity is intentional. That is, the spike may not be a byproduct, but a signal, a marker, a rotating surface panel that becomes visible only when the object reaches a specific alignment with Earth and the Sun. The mechanics are similar to how a satellite's solar panel glints when catching direct sunlight, but in this case, we're talking about a comet-like body, millions of kilometers away, flashing with surgical precision. The implications are enormous. If this is an artificial surface, or even just an unusually symmetrical mineral formation, then it means 3I Atlas has retained structural integrity through solar heating, mass loss, and gravitational tug from Jupiter. That's unheard of. Most objects fragment, spin, tumble, or dissolve. But 3I Atlas continues to present a consistent optical profile, as if rotation was stabilized and the reflective surface is reappearing with rhythmic timing. And here's the most important detail. This latest spike was aimed almost directly along Earth's orbital path. Unlike the first one, which was angled off-center and faint, this burst was clean, narrow, and aimed right where Earth will be when the object's tail crosses near us on December 19th. That's not cause for panic, but it is cause for attention. Because if something out there is rotating with precision, reflecting light with intention, and doing so in sync with Earth's motion, then we're not just watching an interstellar object pass by. We may be watching it align. On December 8th, a new set of high-resolution space environment models began circulating through NASA's internal simulation network. Developed using data from the Deep Space Climate Observatory, SOHO, and the European Space Agency's Solar Orbiter, these simulations were designed to forecast the evolving interaction between 3I Atlas and the heliospheric environment surrounding Earth. The results stunned nearly everyone watching. According to multiple independent models, significant field interference is predicted at approximately 1.6 astronomical units, the distance currently separating 3I Atlas from Earth. That's not the predicted location of a future interaction. That's the distance where the object is right now. Field interference in this case doesn't mean an impact or a direct collision. Instead, it refers to the disruption or modulation of magnetic, plasma, and solar wind structures as a foreign object enters a shared electromagnetic neighborhood, and that disruption is now believed to be not only measurable, but growing. In practical terms, here's what the simulations are showing. First, the region ahead of Earth, the space between our planet and 3I Atlas, is developing a plasma gradient. Think of it as an invisible slope of charge density, building like tension between two magnets being brought closer. This isn't just theoretical. The gradient is already being observed in solar wind velocity readings, which show uneven flow rates along the comet's projected approach vector. Second, models show a potential dipole response from Earth's magnetosphere as early as this week. In simpler terms, the simulations suggest that Earth's magnetic field may begin to stretch or reorient slightly, not because of solar activity, but in reaction to external interference. This is what happens when two magnetic systems begin to sense each other's presence, even across vast distances. And third, the simulations now include what's called a rotational coupling scenario. This is where the rotation of the object, in this case 3I Atlas, begins to generate a rhythmic fluctuation in the space environment around it. If those fluctuations match or approach any natural resonance frequency in Earth's magnetosphere, it could trigger harmonic effects. These effects are subtle, but could influence satellite orientation, signal propagation, or even migratory patterns in animals that rely on geomagnetic navigation. None of this means we're in danger, but it does mean we're now entering an active interaction phase with an object that's still far from Earth. What's more unusual is that the simulations only began showing these interference patterns after the reflectivity spike reappeared. That correlation between optical brightness and magnetic modelling wasn't expected. Some researchers now wonder whether the surface structure responsible for the reflectivity is also influencing charged particle movement, perhaps acting like a capacitor or dynamic conductor in the interplanetary medium. In fact, one of the more exotic models developed by plasma physicists at a European research centre suggests that 3I Atlas may have a layered electric sheath, a kind of floating charge boundary surrounding the object. This sheath, rotating with the body and occasionally ejecting dust or charged particles, could be responsible for the expanding field interaction. Essentially, the object wouldn't need to produce its own magnetic field. It would just need to carry one, frozen in from its interstellar origin, now slowly thawing in the heat of our sun. All of this points to a bigger reality. We are no longer observing a passive body. The distance may still be safe, the trajectory may still avoid Earth, but the space between us, the field, the dust, the particles, is no longer neutral. It's active, it's shifting, and it's becoming unpredictable. This is what happens when something foreign enters a finely tuned system like our heliosphere. We don't just see it, we begin to feel it, long before it arrives. For weeks, the default explanation for 3I Atlas's bright and unusually persistent surface has been the same: exposed ice. After all, most comets, whether from the Oort cloud or beyond the solar system, are made of frozen volatiles. As they approach the sun, these ices vaporize, producing a coma, tail, and reflective outbursts. But after reviewing the latest data from both visual and infrared spectrometry, scientists are now questioning a core assumption. What if it's not ice at all? On the morning of December 8th, new readings from the James Webb Space Telescope, paired with ground-based infrared scans, revealed something startling. The reflectant spectrum of the sunlit face of 3I Atlas lacks the clear water ice signature that scientists expect to see in comets. Normally, solar reflected light would bounce off surface ice and return a distinct dip at specific wavelengths, a kind of fingerprint that confirms the presence of crystalline or amorphous water ice. But this time the spectrum returned a flat, inorganic signature, consistent not with frozen volatiles, but with dense carbonaceous compounds or silicates. That's a problem. Because 3I Atlas is emitting behavior, from outgassing to jet formation to coma pressure, that matches what ice is supposed to do under solar heat. And yet the surface structure reflecting the sun appears to be too dry, too dense, and too organized to be typical comet ice. In fact, the materials now being considered as matches, including layered phyllosilicates, graphite clusters, or even metal-lace basalt, don't sublimate easily. They withstand heat, they hold shape, and they reflect with unnatural symmetry. Which raises the bigger question: how is the object still releasing jets and forming a tail? One possibility is that we've misunderstood the composition of interstellar objects altogether. Rather than being like the fragile snowballs we've studied in our own solar system, these travelers may be more like hollow shells coated with reflective rock, hiding volatile pockets inside. If that's the case, 3I Atlas may not be a uniformly frozen mass, but rather a structured core with internal pressure zones, where trapped gases find release only through specific vents or fractures. But even this model struggles to explain the angular reflectivity and sharp brightness pulses observed. Ice doesn't do that, nor does jagged rock. The light behavior being seen, most recently during the synchronized albedo spike from multiple Earth observatories, points to flat or geometrically repeating surfaces. In other words, 3I Atlas may have facets. That term, facets, is normally reserved for crystals or engineered surfaces, structures that bounce light not randomly, but along defined angles. Some of the recent analyses from spectroscopy teams in South Korea and Germany are now exploring this possibility. They believe the object's surface could contain crystalline metals or fused carbon structures, possibly the result of prolonged radiation exposure in deep space. Over time, bombardment by cosmic rays can anneal and shape material, turning rough surfaces into glassy, faceted reflectors, something that behaves more like obsidian or diamond than ice. Of course, there's another, more controversial interpretation. If the surface is reflective, stable under heat, geometrically structured, and returning the same directional glint twice, could it be artificial? No one is jumping to conclusions, but the timing of the reflectivity spikes, combined with the absence of volatile spectral lines and the measured coherence in its rotation, is prompting whispers across research forums. Some have begun calling it the mirror effect, the possibility that 3I Atlas may not just contain strange material, but be coated in it, like a sail, panel, or even a shell. Whether natural or engineered, the surface of 3I Atlas defies the standard comet model. It does not behave like dirty snow, it does not shine like ice, and as of December 8th, it is officially under reclassification, because if what we're looking at isn't frozen and isn't random, then it might be something we've never seen before, a surface that reflects not just light, but intention. As any astronomer will tell you, brightness tells a story. When a celestial object rotates, it typically creates a predictable rhythm of light and shadow, a pulsation that aligns with its spin. If a surface is irregular, reflective, or ejecting material, these fluctuations become even more pronounced, a cosmic heartbeat, readable from millions of miles away. But with 3I Atlas, that heartbeat is offbeat. Since mid-November, researchers have been tracking the rotational profile of the object. It completes its spin in a relatively stable period, observable via time-lapse photometry across multiple observatories. The cadence is there, the spin is consistent, and yet, as of December 8th, the brightness profile has started to break from that rotation pattern. This is more than a glitch, it's a structural contradiction. In recent observations conducted using both narrowband photometers and wide-field imaging, the object's apparent brightness has begun to rise and fall outside its rotational intervals. That means even when the same surface area is facing Earth, the intensity of light it reflects varies, sometimes dramatically. On one pass, it glows dim and steady. On another, with the same surface facing us, it flares briefly then fades. This inconsistent brightness behavior is not what scientists expect from a passive rotating body. In most comets or asteroids, reflectivity spikes and fades as the object turns. Mountains, valleys, outgassing vents, they all contribute to minor changes, but those changes always loop with each full spin. Not here. 3I Atlas is not repeating its own light curve. Instead, it seems to be governed by something else, something external, or something changing internally with each cycle. Theories are forming, and they're dividing the research community. Some suggest electromagnetic interference could be at play. If the object is passing through varying solar wind densities, or interacting with Earth's extended magnetotail, it could be experiencing environmental changes that affect how its surface behaves. Dust jets might trigger spontaneously, charged particles might scatter differently, but those effects should still fall into a pattern, once normalized across orbital parameters. Others believe the object might contain dynamic reflectors, surface layers or structures that move independently of the core rotation. These could be sheets of material, possibly curled or flexed by internal pressure, that catch the sun at erratic intervals. In this view, 3I Atlas isn't just spinning, it's morphing, subtly reshaping itself as it heats, cools, and discharges energy. Think of a slow-moving gyroscope covered in mirrors, each one fluttering ever so slightly. But the most unsettling idea is also the simplest. The object's brightness might be modulated. In this model, something on or within the object is controlling reflectivity, not as a consequence of natural physics, but by design. The reflectivity spikes could be signals, timed not to rotation, but to some other cosmic clock. They might be directional pings, aligned to external bodies, or worse, responsive emissions, triggered when Earth-based instruments begin scanning. There is precedent for this kind of modulation in human-built satellites. Many probes, even old ones, reflect light unevenly as their solar panels shift. But 3I Atlas is no satellite. It is larger, colder, and far older. If its brightness is changing apart from rotation, then something deep inside the object is reacting, either to space around it, or to us. And here's the real mystery. During the December 8th observation window, the object passed through a low-noise sector of space, with no solar storms, no active flares, and no gravitational anomalies. And still, the brightness spiked again, for less than 3 minutes, with no corresponding change in orientation. This is not how comets behave. It's not even how asteroids behave. This is how systems behave. Complex, sensitive systems that adjust based on input. The light should follow the spin, but this light does not. And in the silence of deep space, that might be the loudest message of all. Comets are fragile. That's been the consensus for decades. These cosmic objects, often described as dirty snowballs or dusty rubble piles, don't just crumble over time, they shatter. When exposed to the heat of the sun or the gravitational tides of giant planets like Jupiter, They often fracture into multiple pieces, ejecting debris in all directions. In fact, fragmentation is so common that many comets never survive their first close approach to the inner solar system. But 3I Atlas is rewriting the rulebook, despite passing through intense solar heating. Despite gravitational disturbances from multiple planetary bodies, despite losing mass at an accelerating rate and showing clear signs of internal pressure, it hasn't fragmented, not once, not even a crack. On the morning of December 8th, new composite images from the Subaru telescope and the Lowell Discovery Observatory were compared frame by frame with data gathered during 3I Atlas's perihelion phase. Astronomers were looking for signs of breakup events, sudden flares, offset trajectories, or telltale signs of a split nucleus. They found none. The nucleus remains intact, its rotational axis stable, its surface coherent. Even after weeks of thermal stress and high-velocity dust ejection, not a single satellite fragment has been detected trailing behind or peeling off. That's statistically improbable. Most solar system comets that reach this level of activity begin to shed material, sometimes explosively, but not 3I Atlas, and that opens a floodgate of questions. The first is structural. What is this object made of? Because it's clearly not behaving like a loose ball of ice and dust. It's resisting shear forces, maintaining cohesion under rotational stress, and surviving repeated jetting events without distortion. For that to happen, the internal structure must be either far denser than we expected, or composed of something other than what we call cometary material. The second question is thermal. Why hasn't it cracked under the heat? As it approaches the Sun, most comet surfaces develop fissures or blowouts due to rapid expansion of internal gas. But the outer layer of 3I Atlas has shown almost no signs of thermal fracturing. High-resolution imagery has revealed a remarkably smooth, uniform boundary, one that seems to flex under pressure but not break. The third issue is rotational. With jets visibly shifting and dust streams ejecting at uneven intervals, the nucleus should have begun to wobble or enter a chaotic spin state. Instead, its rotation remains stable to within tight tolerances, as confirmed by both Doppler radar from Goldstone and time-lapse photometry. That kind of rotational stability suggests mass balance, which is almost never seen in active comets under this much duress. Some are now suggesting that 3I Atlas might have a solid shell, a protective layer that keeps its inner structure contained. This wouldn't be ice, it would be more like carbonized rock or even fused metal oxide. Materials that can take stress, deflect solar radiation, and maintain integrity under bombardment. Others go further, speculating that the nucleus might not be natural at all, that it could be a hollow structure designed to survive interstellar flight, cloaked in comet-like debris. Of course, the scientific community remains cautious. Extraordinary claims require extraordinary evidence. But as of this moment, the absence of fragmentation is the most extraordinary data point of all, because it's not what's happening that alarms researchers, it's what's not. No breakup, no disintegration, no pieces flying off in random arcs, just one singular resilient body, holding shape under every physical stress we throw at it. And if it continues to hold all the way through its Earth proximal phase on December 19th, then we're not looking at a comet in crisis. We're looking at a comet that's built to endure, or one that was never just a comet at all. In the world of celestial mechanics, rotation tells you a lot about an object's past, and even more about its present. Most comets spin up as they approach the Sun, their internal gases heating, building pressure, and venting through jets that act like microscopic thrusters. The process is chaotic but predictable. If a comet gets active, it spins faster. If it starts venting unevenly, it wobbles. If it ejects mass, it reacts. But 3I Atlas is doing the opposite. Since early December, observational teams have confirmed something strange. The object's surface rotation is slowing down, not by much, and not abruptly. But the measurements are clear. The rotation period, which had held stable for several weeks, is now stretching slightly cycle by cycle. The slowdown is real, and it's not following any pattern that we understand. On December 8th, synchronized radar and optical tracking from Goldstone and Mauna Kea confirmed a rotational deceleration that couldn't be explained by natural drag. In fact, there's no drag in deep space in the traditional sense. Comets don't slow down unless something intervenes, like a major outburst, a gravitational tug, or an internal collapse. But none of those things are happening here. The mass loss rate is increasing, yes, but not unevenly. The jets aren't reversing. There's no sign of debris flying in the opposite direction, and yet the surface is rotating more slowly today than it was 3 days ago, according to every available photometric model. So what could be causing it? One idea gaining traction is that the surface of 3I Attalus may have a decoupled outer shell, a crust or layer that rotates independently from the inner core. In this theory, the observed slowdown isn't the whole object decelerating, but rather the visible skin of the comet shifting at a different rate than what lies beneath. If the shell is composed of layered material, or is being actively influenced by electrical or magnetic fields, it might change spin without needing a full-body torque. Another theory focuses on interaction with the interplanetary magnetic field. As 3I Atlas drifts deeper into our solar neighbourhood, it's moving through solar wind channels and ambient plasma streams. If its surface carries a significant electrostatic charge, especially after outgassing events, then it might be experiencing a rotational braking effect as it cuts through fluctuating magnetic vectors. Think of it like electromagnetic friction, the invisible hand of space slowing the spin. But the most controversial interpretation? That the object is intentionally stabilizing. It's a possibility that has researchers split. In spacecraft dynamics, rotation is sometimes slowed deliberately before a key maneuver, like a course correction or orientation shift. Some analysts have begun comparing the data to historical spin-down events recorded from tumbling probes and defunct satellites. The rotational curve, while subtle, looks eerily similar. And here's where it gets weirder. The deceleration began just after the reflectivity spike returned, the same spike that didn't match the rotation cycle. In other words, light behavior changed first. Then spin behavior followed. Coincidence? Maybe. But the sequencing is suspicious. As the object's approach continues, astronomers will be watching this rotational trend like hawks. If the slowdown continues, it could mark the first known case of a naturally active interstellar object reducing its own spin in real time, with no external trigger we can confirm. Or it might be the signature of a layered internal mechanism, a core and a shell, drifting apart in velocity, under the pressure of physics or something else. For now, the only thing certain is this. 3I Atlas is not behaving like a dying comet, it's behaving like a system in preparation. And sometimes the quiet act of slowing down is not a sign of weakness. It's the calm before a deliberate move. Heat, or more specifically, the way a comet handles heat, usually tells us everything about its activity, structure, and stage of life. As solar radiation floods its surface, the outer layers heat up, sublimate, and release jets of gas and dust. That process typically pushes heat inward, warming the core. It's a thermal wave, just predictable, mechanical, and observable. But 3I Atlas is breaking that chain. On the morning of December 8th, a new thermal scan from the Atacama Large Millimeter Array revealed something bizarre. The inner core temperature has dropped, not risen. Despite being closer to the sun, despite active jetting, despite a shrinking coma that should trap heat more efficiently. The thermal energy readings are going down, not sharply, but steadily, like something internal is absorbing or redirecting the heat. This doesn't just defy expectations, it violates the basic comet heat curve model. Under normal solar exposure, the core should be the last thing to cool. Even if the surface begins shedding heat through mass loss or radiation, the dense central material tends to retain warmth, slowly increasing in temperature as energy seeps inward. But 3I Atlas shows the opposite pattern. Its outer layers are warm, even warmer than expected, while its interior seems to be cooling in isolation. One explanation is insulation, that the comet's outer layers are somehow shielding the core from heat transfer. But for that to work, the surface material would need to have an incredibly low thermal conductivity, possibly involving aerogel like dust, porous silicates, or some form of carbon foam. None of these are common in space, especially not in concentrations that would create a thermal wall this effective. But if not insulation, then what? A growing group of researchers is proposing an even stranger model, active cooling. Not passive insulation, but a mechanism, natural or not, within the object that's drawing heat away from the core. That's not normal comet behavior, that's system behavior. The closest analogue we have are cryovolcanic bodies in the outer solar system, moons like Enceladus or Europa, which vent heat while maintaining cold interiors due to internal convection. But those moons are influenced by tidal flexing and planetary gravity. 3I Atlas is alone. It has no partner, no orbit, no spin-induced tidal forces, and yet, the core is cooling itself. More advanced models now suggest that there could be a layer inside the object that transports energy outward, maybe through gas channels, or even a lattice of volatile materials that evaporate internally and recondense at the surface. In this scenario, the comet is acting like a primitive heat pump, an organic machine moving energy from center to shell. That would be unprecedented, but others are going further. A few thermodynamics teams, notably in Prague and Quebec, are modelling the cooling as artificial regulation, implying that the object's core may house something sensitive to heat, something that must be kept cold as the comet nears the sun. If this is true, it would suggest intentional design, not random formation. A payload, a structure, or a system designed to survive transit through heat while remaining thermally protected. And here's the quiet kicker. The cooling appears timed. Just as the rotational deceleration was confirmed, the core's temperature gradient began its downward trend, as if a threshold had been reached, as if 3I Atlas had crossed into a phase where new systems activate. Cooling in space is not something that just happens, especially not at this range, under this kind of solar pressure. If it's happening here, there must be a reason. And if the inner core is cooling, deliberately, selectively, and without an external trigger, then we may not be looking at a comet at all. We may be looking at a vessel, preparing for something. When a comet vents gas, it does so in chaos. Cracks form as sunlight warms the ice, pressure builds, and material escapes from whichever fissure gives way first. The result is usually a messy spray, a turbulent, asymmetrical pattern of jets that flare and fade without rhythm. That's how most comets behave. Nature, after all, isn't neat. But 3I Atlas is anything but messy. For weeks, astronomers have been monitoring the object's active jets. At first, the outgassing followed what appeared to be the standard model: multiple plumes, rotating slowly with the nucleus, expanding outward with the solar wind. But on the morning of December 8th, deep field imaging from the Very Large Telescope in Chile revealed something far more precise. The jets are emerging in pairs, positioned at nearly perfect opposing angles, firing in synchronized intervals and maintaining stable shapes over multiple rotations. This is not how natural jets behave. What's being observed now is a kind of radial symmetry that suggests underlying order. Instead of random eruptions, the jets appear to be spaced like the arms of a gyroscope, launching at regular time intervals and holding their angles with uncanny precision. Even more intriguing, these outgassing events are not correlated with sudden increases in solar heating or gravitational triggers. They're occurring in timed bursts, as if following an internal countdown. And that raises a fundamental question. Is this comet venting, or is it thrusting? The mechanics of the jet formation bear a striking resemblance to cold gas propulsion systems, where gas is expelled through nozzles in opposite directions to stabilize or reorient spacecraft. In low-gravity environments, even a small thrust can produce measurable change. While no measurable acceleration has yet been observed in 3I Atlas's trajectory, the symmetry of its jets implies control, not accident. Some researchers have started to model the object's shape as polygonal, possibly with defined facets or exhaust-like ports that vent at predetermined angles. These models are theoretical, based on the observed geometry of the gas plumes. But if they hold, it would mean the object is engineered, at least on some level, or that it is comprised of internal compartments that vent with perfect structural balance. Further complicating the mystery is the fact that jet temperature profiles are consistent across all visible outflows. This is highly unusual. In a natural object, surface composition varies. One jet might release carbon monoxide, another water vapor, another a mix of dust and organic molecules. But in 3I Atlas, the emissions across symmetrical jets share nearly identical thermal signatures. This uniformity hints at preloaded material, perhaps internal reservoirs that are being depleted in phases, not unlike staged fuel systems. If so, the symmetry wouldn't be a side effect of structure, but a result of intentional staging. One burst stabilizes, the next burst corrects, a cycle that repeats. Even the light curves coming from the jet plumes are symmetrical. Polarimetric imaging shows matching degrees of brightness and polarization across the jets, almost as if the object is emitting with mirror image precision. That kind of detail doesn't happen in rocks, it doesn't happen in snowballs, it happens in systems, and this isn't just happening once, it's repeating. Every few hours the same configuration emerges, not flaring wildly, not decaying, but staying consistent, like a mechanical device doing exactly what it was built to do: hold orientation, conserve stability, and manage energy. Scientists are still hesitant to use the word artificial, it's a heavy label. But the jet pattern is no longer being described as random, it's being described as systematic. And in deep space, when something explodes in symmetry, not chaos, that's when people stop calling it a comet and start wondering if it's something else entirely. Every comet that swings close to the sun leaves behind a fingerprint. It's not just the dust trail or the bright coma or the tails stretching millions of kilometers, it's the radiation echo, a delayed signature of heat and electromagnetic activity that lingers even after the object has passed its closest point. It's how we track thermal inertia, energy retention, and particle behavior. It's how we know the comet reacted to the sun, but 3I Atlas didn't leave one. On the morning of December 8th, an array of solar and deep space observatories began analysing data captured during 3I Atlas's recent perihelion. The goal was simple: to measure the delayed emission spike that normally follows solar exposure. But after cross-referencing infrared, ultraviolet, and microwave readings from the Solar Dynamics Observatory and ground-based instruments in Arizona and Hawaii, no radiation echo was found. That shouldn't be possible. Typically, even small rocky asteroids emit a post-perihelion thermal wave. The sun's energy bakes the surface, penetrates the subsurface, and then slowly radiates back outward. This echo can persist for days or even weeks, depending on the object's size, density, and composition. But 3I Atlas shows nothing. Its radiation profile is flat, not declining, not peaking, just missing. That absence is now being called the silent anomaly. Some scientists first suspected instrument error. Maybe the sensors missed the window, or maybe the object rotated in such a way that the emissions escaped in a direction we didn't track. But multiple platforms confirm the same thing. No post-perihelion glow, no thermal spike, no energy bleed. So where did the heat go? One hypothesis is that the surface of 3I Atlas is unusually highly emissive, allowing it to shed energy quickly and evenly before it could build into a detectable spike. But that would require materials with extreme radiative properties, far beyond what's been observed in even the darkest carbon-rich asteroids. Others suggest the surface could have absorbed the energy and redirected it internally, but that leads to another paradox. The core, as shown in previous readings, is cooling, not heating. Another possibility is that the energy didn't go inward, or outward, but somewhere else entirely. There's growing speculation that 3I Atlas may not behave as a passive absorber of solar radiation, but as an active modulator of energy. That is, it takes in solar input and transforms it, not into heat, but into a different output entirely. Perhaps electromagnetic pulses, or perhaps something subtler, like stored charge or redirected current along field lines. If that's true, then the lack of a radiation echo isn't a failure of heating, it's a conversion event, one that deliberately suppresses thermal feedback, and that kind of behavior is not cometry. It's system level, it's deliberate. Even more intriguing, the last time a similar absence of radiation echo was recorded was with the interstellar object Oumuamua, and that mystery remains unsolved to this day. In the case of 3I Atlas, however, the implications are sharper. Because while Oumuamua was small, dim and passive, this object is bright, large and active. If it can pass through solar proximity, shed no excess heat, and leave no residual energy behind, then it's either the best insulated object ever recorded, or it's doing something we simply don't understand. Some researchers now believe the radiation echo was deliberately suppressed, either by surface design, internal structure, or some unknown process that draws solar energy away before it ever radiates. And that's what disturbs many. Because a radiation echo is not just a scientific curiosity, it's a trail. It's a clue that tells us something was real, present, and changed by the sun. And when there's no echo at all, it forces a chilling thought. Maybe it wasn't changed. Maybe it wasn't reacting to the sun. Maybe it was just passing through, untouched. A comet's tail is its most dramatic feature, a cosmic banner blown outward by solar wind and radiation pressure, stretching for millions of kilometers, always pointing away from the sun. And while the nucleus is small and dense, the tail is vast and loose, constantly growing as more volatile materials sublimate and stream off into space. But 3I Atlas is defying that rule. Its tail isn't expanding, not the way it should. As of December 8th, high-resolution imagery from the Solar and Heliospheric Observatory, along with ground-based confirmation from Chile and New Mexico, shows that the tail of 3I Atlas has remained narrow, focused, and contained, even as the object moves deeper into the inner solar system. And this isn't a new behaviour. It's been like this for weeks. The tail is bright, it's active, but it's not spreading. That's not how natural tails behave. Normally, solar heating increases surface outgassing, which causes the tail to widen, especially after perihelion, when the residual heat causes delayed sublimation. But with 3I Atlas, there's no broadening, no turbulence, no fanning out. The tail maintains an almost laminar shape, like a tight stream from a pressurized nozzle. It's clean, too clean. One possibility is that the material being ejected is unusually heavy, maybe large dust grains or metallic particles that resist scattering, but spectral analysis shows the composition is mostly fine carbonaceous dust and frozen volatiles, similar to what we'd expect from typical comets. Nothing about the mass or size of the particles explains the lack of spread, so if it's not particle weight, then what is it? A growing theory is that the tail is being actively collimated, that is, shaped and narrowed by a guiding force. Some have proposed a magnetic sheath wrapping the object, which could channel charged particles into a straight path. Others point to electrostatic effects, where repulsion forces between like-charged particles create a self-focusing beam. But the most provocative explanation? That the tail is not a tail at all, but an emission, a controlled output, like the exhaust from a propulsion system. The visual similarities are hard to ignore. In multiple images, the 3I Atlas tail appears not just linear, but segmented, with slight pulsing brightness along its axis. This has led some analysts to compare it to ion engine trails, where bursts of material are ejected at constant velocity to produce thrust. In this view, the tail is less like a passive leak, and more like a deliberate signature, consistent, measurable, and aligned. It also raises a troubling implication. If the tail is not expanding, then it might not be dispersing, and if it's not dispersing, then it's likely being emitted in a highly cohesive flow. Which brings us to something else. Deep sky instruments tracking the tail's orientation have noted that it's not always perfectly aligned with solar radiation pressure. It appears to slightly resist wind pressure, holding its shape even when the object shifts. That suggests the force behind the tail is not just reactive, it's stronger than the pressure it should be surrendering to. Something is overpowering the solar, wind, or at least ignoring it. That's not normal. Comets surrender to the sun. That's their fate. They break apart, they scatter, they display their mortality in the form of bright, chaotic trails. But 3I Atlas is holding steady, not growing, not fanning out, just flowing, clean, deliberate, silent. And that has some scientists asking a question they can't yet answer. If this isn't an expanding tail, then what exactly is it? A trail? A signal? Or the exhaust of something alive with purpose? Comets lose mass. That's not a surprise. It's what defines them. As they heat up near the sun, they shed gas, dust, and ice in dramatic fashion, leaving behind tails, halos, and particle trails. The closer they get, the faster they burn off. The process is violent, chaotic, and exponential. The mass loss curve rises sharply with solar proximity until the comet is spent. But 3I Atlas just stopped following the curve. On the morning of December 8th, researchers at the European Space Agency released their latest update on 3I Atlas's sublimation rate. What they found left the entire team quiet. The object's mass loss rate, which had been steadily increasing for weeks, had now suddenly flattened. No more acceleration, no more curve, just a straight, flat line. It's as if the comet decided to hit pause. This isn't how comets behave. Normally, the closer the object gets to the sun, the more volatile materials reach their sublimation threshold. First water ice, then carbon monoxide, then deeper reserves like ammonia or methane. Each triggers a new surge in activity. The mass loss curve steepens with each layer, eventually plateauing only after the object has either disintegrated or vented most of its volatile content. But 3i Atlas is still intact, still active, still releasing dust, yet the total output isn't increasing, it's not even decreasing, it's just static. Some have speculated that the object may have reached a layer of inert material, a crust of rock or carbon that no longer reacts to heat. But spectrographic readings show continued emission of typical volatiles, including freshwater vapour and dust. That suggests the comet is still active, just no longer accelerating. So what's stopping the loss? A few researchers are considering a thermal barrier, a shell of insulating material that slows additional sublimation. But that explanation doesn't account for the timing. The flattening happened right as the object reached a stable jetting pattern and a compressed coma. Too much of a coincidence for many. Others are leaning into a different theory altogether: mass regulation. In this view, 3i Atlas is not passively eroding like a normal comet. It's controlling its own mass loss, holding the release steady at a predetermined rate, rather than letting heat dictate the outcome. This behaviour would suggest the presence of internal controls, mechanisms that meter out materials slowly, evenly, and on purpose. That's not random. That's not natural. It's also consistent with other anomalies observed over the last several days: the mechanical symmetry of the jets, the stable tail structure, the cooling core, and now a perfectly flat mass loss curve. Taken together, these patterns look less like a decaying object, and more like a system that's managing itself. Even more bizarre is that the flattening aligns with multiple other data points that changed at the same time. The surface rotation slowed, the anti-tail grew stronger, and thermal readings inverted. It's as if a threshold was crossed and a new phase began, a mode shift, a programmed sequence. This would make 3i Atlas more than just stable, it would make it predictable, and that's what troubles many in the astronomical community. Because predictability implies design. Stability in space, especially under stress, is not a sign of randomness. It's the signature of a closed-loop system, something with internal logic, something built or born to last. And if the object has now entered a phase where it controls its own rate of decay, that raises a difficult possibility. Maybe 3i Atlas is not here to burn up. Maybe it's preserving itself, holding back, waiting. Waiting. For what? In astronomy, few dates come preloaded with tension, but for 3i Atlas, December 19th has become that day. Not because of an impact forecast. No collision is expected. Not because of a blackout. There's no solar eclipse. But because, for reasons scientists still don't fully understand, everything points to that date. The alignment, the data anomalies, the trajectory inflection point. It all seems to converge. As of the morning of December 8th, orbital modelling places 3i Atlas at a position of maximum resonance with Earth's magnetic pole by the 19th. This means the object will be at the closest point in its trajectory where the angle of its path lines up precisely with the field lines of Earth's magnetosphere. That's not an impact threat, but it is a moment of high interaction potential. Normally, a comet passing near Earth's orbital plane at this distance would be a footnote, a curiosity, a blur on telescopes and nothing more. But 3i Atlas has defied those expectations at every turn. Its jets are coordinated, its mass loss is stabilized, its tail is unnaturally focused, and now it's entering a synchronization window. What does that mean? It means if the object is emitting electromagnetic pulses, as microwave detectors have already hinted, those signals could reach peak resonance with Earth's field in this time frame. Not because the object is targeting us, but because space geometry aligns. When a signal and a receiver are locked in harmonic overlap, strange things can happen. Field scientists are already preparing sensor arrays across the Arctic, where the magnetosphere is most vulnerable. Not because of radiation, but because interference is possible. If the object is active, electrically, magnetically or otherwise, Earth's systems might feel it. Slight fluctuations in satellite orientation, unexpected pressure on high-altitude balloons, even minor geomagnetic shifts could be detected. So far there's no indication of threat, no alarm bells. But what disturbs many researchers is that 3i Atlas has begun to show signs of anticipation, if such a word can even be used for an object. Its behaviour is changing as it approaches that window. The tail isn't expanding, the jets are symmetrical, the cooling core, the muted radiation echo, all point to an object managing itself for stability. And if that stability is being preserved for a specific moment, then what happens after? Some theorists suggest it could activate, that the 19 is a trigger point, either for signal release, structural change, or even fragmentation. Others say nothing might happen at all, that all of this could resolve into nothing more than a remarkably odd interstellar visitor passing through. But those who've tracked the object since its first detection know something feels different. It's not the speed, it's not the brightness, it's the consistency. 3I Atlas is moving with purpose. It resists decay, it modulates its energy, it ignores solar violence, and now it approaches a moment of perfect alignment, not with the sun but with us. For centuries, comets were seen as omens, fiery messengers crossing the sky with no explanation. Science has since replaced those myths with data. But data now brings its own unease, because the more we measure 3I Atlas, the more it looks deliberate. So what will happen on December 19th? That depends on whether this is just a comet, or something far more complex, something observing, something timing itself, something waiting to engage, and if it does, then we'll look back on this moment not as a curiosity, but as the day Earth was noticed,